Hi. Welcome. Well, thanks for coming to the talk. So I've got this deal at the moment where I get a free Apple Watch, but I have to do 12,500 steps every day for 2 years, so I'm just going to walk around quite a lot. It might have been better if I just bought the watch, because it's pretty tough. And I want to talk today about building asynchronous systems and the benefits for doing that. And when you go asynchronous, I want to talk about the benefits of flow control and back pressure. So if you're aware of how TCP works and things like that, then I want to bring that style of application, that style of thing into our application. And I'm going to show some code examples, and I'm going to do a demo, and I'll be using Akka Streams for that. The reason is I work for Lightbend, which is the company that builds Scala and contributes a lot to open source projects, one of which is Akka, and it's my full-time job to work on Akka. So I can't really see you, but maybe if you wave violently, how many people have heard of or used Akka? Yeah, there's some waving, some amount of waving. Anyway, so Akka is a whole set of libraries. It is completely open source under Apache 2, so you can go and use it. You don't need to pay my company any money. The core of it is an alternative concurrency model, which is based on actors. And that was inspired by Erlang. And the idea of an actor is rather than using a synchronous method call into a class or an object, you send an asynchronous method. And you forget about threads and semaphores and locks, and instead the Akka framework handles that for you. And the messages are scheduled, and you don't need to worry about mutual exclusion. You'll only process one message at a time, and you don't need to worry about data visibility, because we'll insert the appropriate happens before relationships between each message. We've also got a lot of clustering stuff. So anytime you want to take your application and start to run it on multiple hosts and address things in a location-independent way. So imagine you had an object in memory for each of your customers, because as requests came in, it'd be too slow to go to the database each time. You can do that with Akka, and you can let your actual requests come into any of the JVMs, and it'll route it accordingly. We've got an event sourcing library, which is basically, it's not a general persistence library, it's for doing event sourcing and CQRS. But the two I'm going to talk about today are HTTP and Akka Streams. So Akka Streams is a reactive streams implementation based on actors, but you don't actually use actors when you do it. It's a higher abstraction. HTTP is then built on top of that, so that the flow control that you have within your application is then transferred to the network level. And that's what I want to demonstrate today, and see the benefit of using a full stack like this. So before that, what type of systems do we like to build? Well, even if you've only got 5 TPS, I'm guessing you care that your system is responsive. And I think you care if your system is responsive for a single request. So it has to come in, and you want to respond within 500 milliseconds or fail. Because we're in the day now where we typically have multiple instances of application running. And being slow is normally worse than being down. So failing quickly is normally favorable to taking a long time and appearing to hang. The more interesting thing, I think, though, is remaining responsive on the load. So if you do your capacity planning and you think that you're going to have no more than 1,000 concurrent requests into your service, but maybe you work for a television company and then the World Cup starts and you didn't quite capacity plan correctly. What happens when 2,000 people log onto your system? And I think systems tend to fall into 2 categories. The first category, which is by far the most common, is to fall over in a heap and no one gets to watch the football game. But what I think we'd rather build are systems that get to their capacity and then start to shed traffic. So you get the 1,000 users happily watching the football, but then the rest of them are rejected, and you give them a 503, or you don't even accept the TCP connection. Another characteristics of system is whether it is scalable. And I'd say there are 2 types of scalability. Let's say you have a fixed amount of resources, 2 gigabytes of RAM, 4 cores. How can you scale your system to allow lots of concurrent requests coming in? And that's maybe more about resource efficiency than it is scalability. And I want to talk about that quite a bit today. The other part of scalability is of going across many hosts. That's where Akka Cluster could help you, but it's not something I'm going to talk about today. So completely technology agnostic, I think we want to be scalable and we want to build responsive systems. Asynchronous programming and an asynchronous execution model is one way to achieve that. And when we talk about being asynchronous, I think it falls into two categories. So first, we've got the programming model. So in Java 8, we've got the completable future. If you're working in a language like Scala, then you've had a feature like that built in for quite some time. Inside the libraries I work on, we've got actors and we've got streams, which I'll show you some examples of streams, not really actors today. You've got things from RxJava. And what they do is enable us to be asynchronous all the way through. We don't have to, but they can enable that. So if you think about your application now, if you go to the database, or if you talk to Kafka, or if you talk to the file system, are you currently using an operating system thread, even though you're just waiting for a response from a database or a response from another service? And if the answer is yes, even if you're using things like futures and actors, then you're not asynchronous all the way through, and you're not going to get the scalability and the resource efficiency that I'm going to talk about today. What we want to be able to do, if we want to be able to use a small amount of RAM, a small number of resources to service lots and lots of requests, assuming that those requests actually involve I/O, so databases, queuing systems, file systems, then what we want to do is we want to do everything asynchronously. There's a problem, however. If you've ever switched a system from being a synchronous thread per request system, say Batey, Tomcat, 1,000 request threads, the benefit of working in that way is what's the maximum number of concurrent requests you could make to your database? Well, it's 1,000. Unless you start kicking off other threads, etc., then you kind of limit how many concurrent requests can come in just by the number of operating system threads that your system is capable of creating. So what happens when you make the whole thing asynchronous? Suddenly, all you do is kick off something asynchronously when the request comes in. That's using a few bytes of memory, 24 bytes of memory for an actor. How many can you currently do? Well, it suddenly becomes millions, which means that when you go to building asynchronous systems, you often end up taking in far too many requests. You end up taking down your other dependencies because you hammered them with far too many concurrent requests. You take your database down, you end up with a very sad DBA. So the other part of the talk, and what I'm going to demonstrate, is how when we move to doing things asynchronously, how do we deal with that? And I'm going to use the terms back pressure and flow control interchangeably. And what they essentially are is how quickly do we allow requests to come in? If we've got two parts of our application and there's a queue in between, how quickly do we send messages across? How quickly do we read data coming back from the database that needs to go end up at a user request? Can we base how quickly we query the database off how quickly the client is consuming the bytes from the socket on the other side? So the takeaway is hopefully going to be that you'll understand the benefits of things being asynchronous if you don't already know. What will flow control give us, and why do we need it if we're going to build asynchronous systems? I will briefly mention the Reactive Stream specification. That's going to become much more important when we start having JDK HTTP clients and database drivers that are Reactive Streams compliant. And then the final bit of the presentation, which will be primarily a demo, then I want to just show you how you do this in a library like Akka, and hopefully that'll mean that you can take it away and you actually believe everything I've said. So, the use case. When I do the demo, we're going to use two endpoints. They're going to be quite simple. The first one, I'm going to demonstrate an asynchronous web app for us. So it's going to be just getting a small amount of data from the database. And that's just going to be a small amount of user information. And the relevance of it being small is that we're not going to use any flow control. We're just going to have as many as we want coming in. And we're just going to show that with a small number of threads, say 4 threads on my laptop, with the database running on it as well, we can handle many hundreds and thousands of concurrent requests. The second endpoint that I'm going to demonstrate, that is going to be, imagine that you keep track of everything your customer did, but you probably had to throw it away now because of GDPR. But imagine you still had that data, and then suddenly you could request it, but it's a very unbounded amount. Some customers might do 4 things and then decide that your web app is useless and never log back on. Some of them might click every button or create an IRC or a Slack bot which hammers your service, and they end up doing millions of things. So I've got a little small database running Apache Cassandra on my laptop, which I'm going to use, and it's got many gigabytes for certain users. So we can make a request in, and then we're going to show how that we're going to use a very small heap, and we're going to change how quickly the client reads the data and see that flow all the way through to the database. And we're going to hope that it's going to respond in a good time, even if it's a failure. One of the side effects or the other benefits of building things which are flow controlled is that we're not going to do any unnecessary work. So if the client that comes into our application stops consuming the response, we'll stop doing the computation. We'll stop pulling the data from the database. We're not going to do things under the hope that the client's going to start reading that response back. And we're going to hopefully do this in a constant memory footprint. So whether there's 10 records coming back from the database or 100,000, we're not going to require a bigger heap. So how do we do it? Well, the first thing we need to think about is our execution model. Right? So we need to think about the threads in our system. And if we think about the simplest execution model that we've got for JVM applications, it typically maps a user request into an operator or into a Java thread, which is typically an operating system thread. So if a request comes into our application, that's normally mapped to a method invocation. Imagine this thing called perform task. We then block that thread regardless of what we're doing. Now, if we're doing something CPU bound, then this is a good execution model. But if we're going to start doing things which are network bound and database and HTTP calls, then this is going to start to be a problem. Because if we want to execute lots of different tasks, then they're all going to be blocked one after another. So what do? Well, we think, let's try and make this asynchronous. So if you've not seen an actor in Akka before, this is what it looks like in Java. And it looks a lot like the previous one. I mean, we've got this builder API, which says that when I receive a message of type task, I'm going to execute this code. But the code below, which calls it, that is non-blocking. So you say actor.tell, and it will send it, and it will be asynchronously sent. So we could kick them all off, and we could send them to different actors. It would be the equivalent here of kicking off different futures or things to different thread pools. However, the problem will be is what happens if 1 million requests come in, and all of them send messages to an actor? Or we kick off 1 million futures. And that's some of the problems we're going to try and solve today. So let's think of something a bit more concrete than a task. Let's think about a web request. What is a web request? Well, it's kind of a function from HTTP request to HTTP response. What do we do during that? Well, we might pull some things out. We might get some things from the requests, like query parameters, path parameters. We might go to a database. We might go to an external service. And there are 2 kind of problems with using this type of execution model. The first is the blocking, which I've already spoken about. So the fact that even though a lot of this is just I/O bound, we're wasting quite a valuable resource, as i.e. a thread. But the other is timing out. So if you make a call to JDBC, or you make a call to your favorite HTTP client, and you've got some kind of agreement that you want to respond to this request or time out within 500 milliseconds, how do you do that with this execution model? I mean, maybe you can set timeouts on your HTTP client. Maybe you can set timeouts on your database drivers. And typically, these things end up mapping to socket-level timeouts. So you end up with like TCP receive timeouts, TCP connection timeouts, which don't quite marry up to what your requirement is. Because if you're getting a big chunk of data back from a service or a database or a queuing system, the TCP receive timeout, that's just going to be the amount of time we wait for any amount of data to come back. It might be 1 byte, whereas your whole response might be spread over lots and lots of packets. So it's quite hard to build a responsive system when we're using this execution model. Libraries like Hystrix, when you're using them in the synchronous mode, what do? Well, they shove the request on an entirely different thread in a different thread pool, meaning that you get a future back, which means that you can time out independently. But what you've done there is you've started using 2 threads rather than 1 thread. So what's the alternative? Well, the alternative is not to think of a user request or a HTTP request as a function from HTTP request to HTTP response, but think of it as a HTTP request to some asynchronous construct of HTTP response. And this example in Akka HTTP, when you're not using streams, that would be a completable future. And there are a couple of benefits to that. The first is, what you're planning to do when implementing this post method is to quickly build up a recipe for the response, rather than actually doing the work, and then return it to your web framework or your web library. And then the library can put a callback on that and decide when to actually send the response back to the user. Which means it's quite easy for a library like Akka HTTP to time out independently, just to give up waiting for your future. We don't need to worry about wrapping it in something like Hystrix. It also gives us the option, if all of our dependencies, like database clients and HTTP clients, if they're also asynchronous, it gives us the option never to block on I/O. Whereas with the previous execution model, we couldn't really have done it. It does add some complexity, especially on the programmer. So for instance, here's an example of, I probably haven't said this yet, but all of the code from here is scraped from the project which I'm going to demo. So this isn't just typed in code into the ID, into the whatever presentation it is, actually code that's you're going to see later. So basically, we now need our lookup to the database to return a completable future. We need ways of composing things. So when we end up with one asynchronous computation, we might need to kick off another asynchronous computation, which is on the CompletableFutures API is then compose. Or in the Scala future API would be flatmap. And then that's real. This was my fictitious web server. This is real Akka HTTP code. So I'm saying we can go to the database, we get back a user. Maybe that user doesn't exist, so I've also put this in an optional. And then this onSuccess method is actually Akka HTTP code. So you give it to Akka HTTP, and you say, I'm not going to give you a concrete object, I'm going to give you this future back. Here's the same example in Scala, because it looks slightly nicer with the request directive, which is called with request timeout. So it's very easy for us to offer this type of functionality, because now we're basically just racing two futures. We're racing the future that you've given us versus the fake future, which is coming from the with request timeout. And when we do the demo later, if I do it on a cold JVM, some of the requests might take more than 500 milliseconds. So we're going to get some 503s back from Akka HTTP. So that's asynchronous, and one model of doing asynchronous for something like a web request via something like CompletableFutures. The next section is trying to remain responsive under load. And a lot of the time, it's about just playing fair with our dependencies. So if you think of the systems you build, a request comes in, and maybe you're going to go call to another service, or you're going to call to a database. Do you ever stop to think, you being the JVM, your code that's running, do you ever stop to think, should I really make this call? All right? Should I really do it? I already have 1,000 outstanding requests. Should I do 1,001? So anytime you think about this, just think about it as like a producer or a client sending a message. That message might be a synchronous request. It might be an actual asynchronous message. We just need to think, should we be sending it? Is the downstream capable of handling it? How many should we do? If this is actors, it would be, how many messages should I send to this actor? If it was futures, like in the previous example, how many outstanding futures should I allow before I think, oh, I better stop? And I think often the default is to start and we add some requests and we start sending messages and we start to catch the fish. And then inevitably, a big spike of traffic happens and bad things happen. And I'm sure you've all had the system where you had that unexpected load, and it often manifests itself in JVM applications because we've got lots of queues and often unbounded queues. Then we end up with an out-of-memory error. So one way to think about how you would design a solution for this, and we're going to end up at flow control, is to think, what would you do if you just put Kafka between everything? Well, you'd not worry about it because Kafka can store a lot of fish. However, in this example, if we have a persistent buffer between all of our asynchronous boundaries, then of course, if we have a faster producer and we have a slow consumer, then of course it can just buffer up. Has anyone ever filled up their Kafka? There's a few, not many. But most of the time, we don't have a durable, persistent queue in between our asynchronous boundaries. Like, you can't put Kafka in between your JVM application and your database. You can't put Kafka in between your JVM application and Kafka. Right? That just wouldn't work. Or within different parts of your application. So we need a way to be able to decide at what rate we should do stuff, where stuff might be database requests, messages, whatever. And something which has become quite popular is circuit breakers. And I've mentioned Hystrix a couple of times. That's one implementation. In Akka, we have circuit breakers as well. So if you've not come across these, what they are is you decide what your asynchronous boundaries are, or your risky things, and you wrap them in something which keeps track of how often it fails or how often it times out, and you eventually cut it off. You say, this is failing too often. I'm going to give my downstream, that other part of my system, I'm going to give it some time to recover. Is that the best we can do? Because what we're really doing there is reacting to failure. Whereas what we really want to do, I think, is be proactive. We don't want to kill our downstream dependencies. We don't want to overload other parts of our application. We want to have we want to communicate with them and agree on an acceptable amount of load that we don't want to hard code in configuration. And that is what flow control is. So flow control, which is built into Akka Streams, it's built into anything which is Reactive Streams compliant, is about dynamically adjusting the rate based on demand. So if you think of any type of interaction in an abstract way where you've got a producer and you have a consumer, there's always some type of buffer. The buffer might be of size 1. And rather than the producer of requests, the producer of messages, just doing whatever they want, I'm just going to send as many as I like, it has to wait for demand to come from downstream. So in this example, the consumer has a buffer of 5. It has 4 items left. And what it's going to do is it's going to send a request message to say, I've got space for 4 more. And then the publisher, if the publisher's got 6 ready, he can send 4. If he's got 3 ready, he can send everything. So it allows the publisher to go as fast as it can, but then the publisher has to stop as soon as the consumer has not given it enough demand. So the question can be then is, what do you do if there isn't demand? Do you not accept the TCP connections? You send back 503s. You can drop it. You can archive it. But you have to make that decision. And sometimes we're not very good at making that decision, because imagine going to your business and saying, what should I do if user requests come in, but there's no demand? And you'll be like, well, we don't want to reject user requests. That sounds ludicrous. But the alternative is things ballooning up until they explode. And this pattern came about in so many things like Akka applications and things like using other asynchronous frameworks that eventually it was somewhat standardized in Reactive Streams. And that is basically the formalization of that protocol so that Akka can do this, but then we can also interact with other things that can do this, like Reactor and Monix. And if you think about that actor which I showed you originally, the thing it's deciding is how quickly we should send messages to it, except we want a nice fluent API for it. And Reactive Streams has been around for some time. It's back in 2013 when it was originally thought of. And then it's actually, the interfaces for it made it into JDK 9. So I'm about to show you the Akka Streams APIs, which is nothing like Reactive Streams. But then if you want to hook up Akka Streams with someone else who's doing a similar thing, you can ask us for a standard interface that you can then pass into the other system. And before Java 9, it was part of a library, so you don't need to be in Java 9 to do this. So let's see what Akka Streams look like. So we're not going to look at actors, we're not going to look at futures again, we're going to switch to something which is flow controlled. So that's the benefit that we're hoping for. So to understand Akka Streams, you need to know a few bits of terminology. And the first 3 are sources, flows, and sinks. So sources are where things come from. Bits of data, messages, HTTP requests. Sinks are where they end up. An example of a source might be a Kafka topic. It might be a TCP connection. It might be a HTTP endpoint. It might be a database table as you're watching for rows and then coming into your system. Sinks are much the same thing. They could be Kafka topics, they could be database tables, but instead of getting things out, we're putting things in. Everything in between is a flow. So flows might transform and map and deduplicate, or, call out to another HTTP service and somehow augment the things going through the flow. And the really important takeaway is that anything upstream, So in this example, when we have a source, when we have a flow, is not allowed to push elements down until demand has come the other way from the sink. And all of this just happens under the covers, so you don't need to worry about it when you're programming with Akka Streams. It's the type of thing that you would end up encoding in actors and futures and things before some things like Akka Streams came about. So before we go into the full example, which involves HTTP and databases and all sorts, let's just look at a really simple example. So this is about as simple as it gets for an Akka Stream source. It will range from the elements from 0 to 20 million. But it's not going to manifest itself as bringing a collection into memory of 20 million elements. It's just a recipe for producing elements. The simplest flow I could think of would be something which turns an object into a string. But flows can be really quite complex. You can have an outbound TCP connection as a flow, which every time something comes in, it sends it out to TCP, and then anything that comes back is then sent down the flow. The simplest sync you can pretty much get is a side effecting for each. So every single element that comes into it, it prints it out. You can imagine that a for each sync is able to ask for things very quickly because it doesn't really need to do anything. It's not waiting for a database or a queuing system to acknowledge things. If we look at the types of those, so sources and sinks have two type parameters. The first one, which is probably what you might expect, is the type of the elements that the source produces or the sink consumes. But there's also this extra type parameter. So in the sink, it's a completion stage, which is a subset of a completable future. And basically, any stage or operator that has been built or you build for Akka Streams, you can also materialize an extra value that you can use to interact with the stream from outside of it. Because once we run this stream, it's just something happening over there. But here, you get back a completion stage which says, which will complete when the stream has run out of elements. All of this is just a recipe. So unlike a completable future or a Scala future, which is eager, as soon as you kick it off, it starts, you can reuse these bits of code. And then you wire them together. So I can say I want to go from this source via this flow to this sink. And it still hasn't run. It's only when you call .run. And that requires the actor system to be around, and it will be materialized as actual actors. If you've seen, that's the Java version. This is the equivalent Scala version. We try very hard to make the APIs look very similar, but try to be idiomatic to the Scala language and the Java language. So you can see it's really quite similar. A few less parameters because it uses implicits under the covers. Both of these can be even more concise, so this is the same program in 1 line or 3 lines in both Java and Scala. So materialization. So you build a recipe, and then you run it. And the running is done via actors. And this is where the flow control and the demand comes in. So if we were to take a very simple Akka stream, which is ranging from elements 1 to 3, we do some mapping, and then we use a sink which reduces it, so it just takes one element at a time and applies the function. If you were to run that, it would turn into one actor, and there'd be no asynchronous boundary, and there'd be no flow control whatsoever. But as soon as we've got anything asynchronous, so you can explicitly ask for an asynchronous boundary inside Akka Streams. And as soon as you do that, we'll end up with 2 actors running it. And as soon as you've got the asynchronous boundary, that's where the flow control happens under the covers. So the first part of the stream, which is the source and then the map, is not allowed to produce elements until the second part demands them. And it's at those boundaries where you could plug in another Reactive Streams library. You could plug in a Reactive Streams HTTP client, or you could plug in like a database driver or something like from RxJava. Now, if you know about TCP, you'll say this sounds very familiar. So one of the benefits of using, say, Akka HTTP with Akka Streams is that we make sure that that same flow control is then applied to how TCP does flow control. So a little primer, and we're going to demo this soon, is with TCP, it's a two-way communication pipeline. So as soon as you establish a connection, client can send to server, server can send to client. It's almost irrelevant who established the connection. And there are 2 buffers involved, because the operating systems like TCP stack, it will have a receive buffer, a send buffer. So when your application sends, it will go into a buffer. It'll then be sent to the server side, and it'll be in another buffer. And then eventually the application has to read it from that buffer. And the size of that buffer is advertised to the other side. So in my very small computer, something smaller than a Raspberry Pi, we could say that that buffer size would be 4 bytes. And that's advertised during the initial handshake. If we send some data across TCP, so let's say we're making a HTTP request, and the other side has not read it from the buffer, then TCP will then advertise the window to be smaller. And what we want to do is when this happens, we want to make sure that our application is aware that this is happening, and we slow down. And if you open up something like Wireshark, then that will show, you can see very clearly when this happens. So Wireshark is a tool which we'll use during the demo, you can see the TCP packets going back and forth, and you can see the TCP window is being advertised. And if you can't see this, I'll zoom in when we do the demo. The black and red bit is saying that the TCP window is full. So anytime we see that in Wireshark, we want our computation to stop inside our server, because the client, whoever's meant to be reading this data, is not actually doing anything, so we shouldn't be doing anything. Another tool that we're going to use while we're doing the demo is socket statistics. So those buffers, they're bigger than 4 bytes, unsurprisingly, and we're going to use SS. And because I'm going to be running the client and the server and the database all on my laptop, we're going to be able to see both sides of the TCP connection. So we're going to see the HTTP client, we're going to see the HTTP server, and we're going to see the send and receive buffers on both sides. So it's about time we put all this together. So the example is going to be a HTTP client talking over TCP to a HTTP server, talking over TCP to a database. And what we're going to be able to do is control how quickly the client is consuming the data. So it's going to be a very weird client. It's not just going to be a load test tool doing it, or it will be for the first one, but not for the second one, so that we can see that our client and our server application, our database, stop doing things when we stop doing demand. So I'm going to show you a little bit of Akka HTTP code just to give you some context, but we'll look at it more in the IDE. Another thing we're going to use is a connector for Apache Cassandra that is open source and in a project called Alpaca. So Alpaca is a set of Akka Streams sinks and sources, but for external systems like Kafka and RabbitMQ and Apache Cassandra and HDFS and all sorts. So what does an Akka HTTP client look like? Well, we can make a single request and we get a future back. So that's the first little bit of code. I'm showing you the lowest level API here where we're dealing with byte strings, which you can think of as byte buffers or byte arrays directly. However, that completes when the connection is established, we send the request, we get the headers back, the future will then be complete. But it doesn't bring everything back into memory. It doesn't try and read everything from the socket. If you look at here inside the map, so on the third line of the second snippet, if we actually try and get the response coming back from the server, it comes as an Akka Stream source. Now, if you remember, a source is not allowed to do anything until there's demand from a sink, right? Because it has to wait until the sink's got capacity, whatever that sink might be. So if you're using the Akka HTTP client and you're dealing with large payloads, then you connect it to a sink, which will only demand it when you want the data to be pulled from the server. So the Akka HTTP server, so on the server side, we're going to bind to a port. That's not very exciting. But the signature of bind and handle, I think, is quite interesting. Because the thing that you pass in, the traffic to serve from Akka HTTP, is a flow from HTTP request to HTTP response. And there are routing DSLs which we're going to use, so you don't need to deal with that at the low level. But you could have full control over how quickly to take the HTTP request from Akka HTTP. So the routing DSL, don't worry too much about it, but we're saying from a path user /tracking/name. And what we're going to do is we're assuming that we get a source back from our database layer. So we're going to talk to Apache Cassandra. We're going to get a source back, which is a source of data, which is going to come from the database. Now remember, sources aren't allowed to produce elements until the sink demands it. But we give that source back to Akka HTTP. And then what Akka HTTP is going to do is connect it to a sink, which is tied to the socket, the TCP socket, which is going to send data back to the client. So until there's room in our send buffer on the TCP side, we're not going to ask for any elements. We're not going to ask for items from the database. So if the client stops consuming things, we're going to stop demanding things from the source that this code has produced us, and then we're going to stop taking things back from the database. Cassandra source is quite simple. It's from Alpaca. It turns a Cassandra query into a source of database rows. You can then map them, and you have things like map and flat map and filter. I'm just mapping it into a little Pojo called event. So time to demo some of this stuff. So I'm just going to displays. It's going to mirror my screen so I can see what I'm doing. Let's hope this doesn't blow everything up. Keep. Right, so let's go into the ID. How can we see that? Can we get rid of me so we can use more space for the screen, maybe? Nope, hopefully you can see that. Right, so let's start off with the server. So these little things like bind here, that was my thing which took it and grabbed it into slides. So if we have a look at the Akka HTTP server, we're going to have a root. A root it's concatenated out of many roots. The one we're going to care about first, we're going to do the asynchronous one, then we'll do the streams-based flow control one. So what do we do inside a user root? Well, this is the thing with the request timeout. So if this future that we give back to Akka HTTP doesn't complete within an appropriate amount of time, which is 500 milliseconds in this case, we're going to send back a 503. And the Akka HTTP library will do that for you. All we're doing is making a lookup to a database. It's quite simple. The Apache Cassandra API is asynchronous. It's based on Guava listenable futures. So it's quite easy for us to turn that into a Scala future. So I'm going to run the server. And then I want to generate some load. So I've actually, if I show you the run configuration of the server, I've given it a small heap, so 256. I've configured it to use a very small number of threads, so Akka picks its threads based off the number of cores, and I've got 8 cores on this laptop. I'm going to connect in mission control, which should be there. Oh, yeah. Oh, I've gone. And mission control, hopefully you can see this. We can see the amount of memory we're using. I'll try my zoom. Is a very small number of megabytes. Number of threads that we've got. So, of course, the JVM has all sorts of different threads. I'm just going to put a query in here, which only shows the Akka threads. So the one's actually doing stuff. This would be the equivalent of your Jetty or your Tomcat threads, your actual request threads. We've got this pinned one, but the one we actually care about is the Akka dispatcher thread. So that's where your code is going to execute. And I've got a little load test tool. So we're not going to do flow control yet. We're just going to use a load test tool called Gatlin. So if you do load testing on your applications, what does a load test application do? It makes requests and it waits, right? It's about as async an app as it gets. All it really does is block on I/O. However, a lot of our favorite ones on the JVM, like JMeter, they map a user client to be a operating system thread. So if you need to simulate 500,000 users with JMeter, how many threads do you need? 500,000. How big a box do you need to generate that? How many machines do you need to generate that? This one I'm using here is called Gatlin. It's an async load test tool. I find it quite useful, so it's worth checking out. But this isn't a talk on Gatlin. It has its code defined in Scala again, so I can basically say I'm going to execute a request. I'm going to go /user/ch Batey, so this is the small request. And then I'm going to inject users. So I'm going to inject 400 users per second for 60 seconds. But I'm only going to allow my application to have 8 threads, but I want to be able to handle like a lot of requests. I've also got Apache Cassandra and things running, otherwise I could do a lot more. Just making sure I have. Yep, Apache Cassandra's up. So I'm just going to Control-Shift-9, and I'm going to run this from the command line. Right. So I've got a little script called run Gatlin. Let me just zoom in on that. That's basically just sticking something on a class path, running the Gatlin script, and then this is the scenario, the apply load. I'll make that a bit bigger just in case. So we're going to run that. Hopefully it's going to run. So we got some 503s right away. And then it gets going. So it's going to print a summary. It's also going to make us some pretty graphs at the end of the presentation. We've got 4,000 requests, 5,000. That's going to go for a minute. So we're doing what we expected. But if we go back and we look at the amount of memory the application's using, bearing in mind the only thing this request is doing an asynchronous request to a database. We don't really need any computation resources here. Then we're hovering well below 80 megabytes of RAM. And if we look at the number of threads, Akka's created up to 8 threads because that's the max. But we're still being able to service a lot of concurrent requests. And hopefully I've talked for long enough that that'll be finished and we can prove that. This is going to go. We're up to 20,000 requests. What else? 60 seconds is a long time in a demo. Should have done 30 seconds. Okay, so that's done. And we can open that up. So if you've not seen Gatlin, it comes with fancy UI tools, so managers will like it. We've made 24,000 requests. We had 8 fail, because obviously as the JVM, I just started that JVM, so the first few requests did not respond within 500 milliseconds, so we got some 503s. But then we steadily started serving the traffic quite easily with a very small number of threads. So you could run a really small JVM running this application inside a container inside Kubernetes or whatever the hip kids do now. Right, so that's asynchronous, but the more interesting thing is flow control, because they were really small requests. What I want to show you is a more exciting application. So that was just load test tool hitting a asynchronous web app. Right? What we want to do now is include an extra client and then be able to control the demand at which things come. So I've got a really silly application called client driver. Right, so if we were to just run against the endpoint, which serves many gigabytes of data with this small heap, it would complete very quickly, because it would just stream it all out. And what we want to do is demonstrate the flow control. So what I need to be able to do is to control how quickly we read things from the socket on the client side. And we've got a set of utilities inside Akka that allow you to test your streaming-based applications. And so we've got a test sync. And the test sync here, which you'd normally ever use in a unit test, allows you to call things like request and to request demand. So you could test your Akka Streams-based application. But what I've got here is an application. It makes the HTTP request out. We get back the future of HTTP response. And then from that, we get a source. So the actual response is in a source. We then do some JSON parsing, and we parse it line by line, and then we return that. And inside the client driver, all I do is read a line from standard input, which says, how many would you like to request? And then I have a for loop, which just requests that many. So if I start this, it's going to create the HTTP connection, it's going to create the TCP connection, connect to the server application, make the HTTP request, but we're not going to give any demand. We're not going to request any of the results. So what would you expect to happen if we do this? I'm just going to start Wireshark and things. So there's nothing there yet. I've also got, this is server sockets. It's cut a bit off. No, it hasn't. Okay, so what I'm doing here is I'm going to show TCP connections going between ports, any port, and port 8080. So when I start the client application, I should see that. So nothing's happened. If we go back here, what we've got, and I wasn't quite quick enough, is we've got the TCP connection established, and we can see it from both sides, because the client and the server is running here. And then the receive buffer of the client is full, and the send buffer of the server, which is this one at the bottom, is also full. So we have done some stuff. The Akka HTTP server and the Akka HTTP client were allowed to do things until the operating system said, nope, the TCP buffers were full. And I've actually got a printout. So every time we ask for more rows from Cassandra, I print out a line. And it's printed out lots and lots of lines. It doesn't matter what it is. It just says fetching more results. But it's completely stopped. And if we were to go into Wireshark, we'd see this stuff here, which is the TCP push. That's basically some data has been sent. So we sent loads and loads and loads and loads until the TCP window filled up, and then we stopped. So right now, the TCP connection's still there. We're just not actually reading the data. It's simulating the client going slowly. But what we can do is we can go to the client, and we can request it. So as I said before, this is a silly endpoint which like returns events from what users might be doing. So I've requested the events for me. So let's see what I do. Well, I go to the shops, I buy some crisps, I eat some crisps, I nap, and I keep doing this over and over again. But it is new data. There's many hundreds and hundreds of megabytes or gigabytes inside the Cassandra database, and this will go on forever, because I could ask for 1,000. And I just keep doing the same thing over and over and over again. But because I've requested 1,000, that's allowed our Akka Streams, our Akka HTTP application, to start reading, which has meant that Akka HTTP client has started reading from the socket again. So if we go to something like Wireshark, we'll see that the window is full, and then TCP heartbeats, saying that the window is still 0. And then it started up again. So our application has started working. We've sent some more data because we consumed some, but quite quickly, because I only asked for 1,000, I only asked for a relatively small amount of data, the window's full again. And I could go back in, I could ask for 10,000, I could ask for even more. And this time, we'll try and sneak back into here. No. So what I wanted to see there, but didn't, was the fact that we would see the TCP buffer's been drained, and then them fill back up because I didn't demand enough. So let's ask for even more. So we're going to request more and more and more, and there we go. So there's the drains, but because I've stopped requesting things, the TCP buffers fill back up, and our Akka application on either side stops doing anything. Another thing we can do is show is the fact that if I press enter a few times, so I print out this thing every time I'm interacting with the database. It's this API where you say, I want to kick off an asynchronous request, and then I tell it when I should fetch more results, but I do it in an asynchronous way. So I'm not doing anything with Cassandra, but then if I ask for another 1,000, and I quickly go back, nope, I must have more. Maybe I've got them all. It's not going to do it. And then we start kitting back. So if you think about how far that flow control has traveled, it's traveled from my client application over TCP into the server application, and actually affected the way in which we query the database. Right. So that's it for the demo. We've got a couple of minutes left. So I hope that was clear what was going on during the demo. If not, do come and ask questions. But what the second demonstration showed, making a request for a large payload, the TCP buffers filling up, and when those TCP buffers filled up, the server stopped doing work. And then as we demand more, and as our clients start doing things, then everything started working again. And that's everything I've got time for today, so I want to thank you. All of the slides and all the code and the demo and how to run the demo and how to look at Wireshark and SS is all in that repository. So thanks very much for listening. Thank you.